Hi, so in this video I want to bring several different concepts we've been looking at together, and in doing so answer the question, what is pressure? And through that we're going to start looking a little bit at a branch of physics which is very applicable across lots of other sciences as well, which is thermodynamics. So the starting point for this is a problem we did quite a while back now. We did this problem about a rocket sled. If you recall, we were looking at what happens when a force is applied for a fixed amount of time, and how does that produce a change in motion. And so from it, we did this little calculation. We'll go through it again, but we come up with this set of graphs that show the acceleration changes with time like this, the velocity changes with time like this. From that, we looked at the force time graph, which you see matches the acceleration time graph. We, following this problem through, worked out the ideas of impulse and momentum. So if you remember the mass times velocity before minus the mass times velocity after equals the force times how long it was applied for, and it corresponds to kind of the area under this graph. So we looked at this concept of momentum, and we saw that it was really useful for looking at situations such as a collision, where it's very, very difficult to determine exactly what the internal forces within that collision are, because they kind of change during the collision. So the idea is that the change in momentum, the momentum is mass times velocity, and the change in momentum gives you the force times the amount of time it was applied for. Now those forces can be kind of complicated. They could get bigger and smaller during that time. So this is kind of the average force. Now there's another way that we can kind of turn this a little bit on its head, and instead of looking at the change in momentum, we can use a known change in momentum to work out what an average force is over a particular time. So an almost alternative definition of force is that it is the rate of change of the momentum of an object. So if we look at it like that, the force equals the change in the momentum divided by the amount of time that change in momentum took. So we could say mass times velocity initial minus mass times velocity final minus mass times velocity initial divided by the amount of time it took that change to take place would give us the average force. So what has this got to do, though, with fluids and what we were just looking at? Well, we were looking at this concept of pressure, and I introduced the idea that where pressure comes from in a fluid is that it is collisions of those molecules with the walls of the container, and also with whatever else happens to be in the fluid. So what's the connection to momentum? Well, every single one of those collisions changes the direction of motion of the atom. So you can follow this little one here. It starts off in this direction. It hits the surface, it bounces back up, it hits this surface here, and in each case it has hit that surface, and there's been a force perpendicular to the surface at the collision site, which has changed the momentum of the particle. So every collision produces a momentum change in the particle, and because Newton's third law says that there has to be an opposite force, if that force was exerted on the particle, it has to also be exerted on the wall. So each of those little collisions adds up to the total force that is being exerted on the wall. So by looking at that momentum change, we can try to work out what that force would be in any given situation. So let's look at kind of a simple setup here. I've got a cube or a square box, cube box, 3 dimensions, x, y, and z. And the area of one particular end, we're going to look at this far end on the right hand side here, is A. So the sides of the box have a it's a sealed box with a certain volume. It has n molecules inside, has some number of molecules inside, fixed number, and each of those molecules has a mass n. So we've got like a bunch of identical spherical molecules inside this fixed volume. So if we were to kind of analyze that, we would be able to see that they're all going to be moving at different speeds. And so we're going to be able to say there's like an average speed. We kind of look at all the different speeds and somehow work out what the average speed is. So the average speed we're going to call v with a little bar over it. But there's going to be average speeds in the x, y, and z directions as well. It's all completely random, so they're probably going to be equal to each other. So we're going to have average velocity in the x direction, average velocity in the y direction, average velocity in the z direction. So each time there is a collision, and we're going to look just at this end wall here. So we're only looking at molecules that are moving in the x direction and then being reflected. So they might be moving in the y and z direction as well, but the bounce, if you like, is happening in the x direction. So each one is going to come in with an average x velocity and bounce off, and it's going to leave with the same velocity. We're going to assume these are perfectly elastic collisions, which means there's no energy loss. The kinetic energy stays the same before and after the collision. So what is the average momentum change per collision with that end wall? Well, pretty obviously the y and the z directions of the velocity are not going to change at all. There's no force in that direction. The only force is going to be in the x direction. So the average change in velocity is going to be 2 times the mass of the molecule times by the average velocity of those molecules in the x direction. So the reason it's 2, of course, is because it goes in with positive some velocity and out with negative velocity. So the overall change is twice the initial velocity. So this is our average momentum change per collision with the wall. So if we're going to work out the amount of force that corresponds to, we need to also know how many of those collisions are going to happen within a particular amount of time. Let's call that time delta t. So on average, how far away from the wall could a molecule be and still hit the wall at that particular time? So if you think that, a molecule right over here, depending on how long delta t is, might not have enough time to reach this wall. So you're going to be able to kind of draw a little sub-box, and only things which are a distance average velocity times delta t are going to be within range of the wall within that time. We're going to kind of measure the number of collisions in this time delta t. Only molecules that are in this little slice are going to reach there at that time if we assume they're all traveling at the average velocity. So this is how far away a molecule has to be in order to hit that wall in that time. So how many molecules will there be in that time? Well, really, if they're evenly distributed, all we need to know is the volume of that little pink bit there. The volume of that little pink bit is going to give us the number of molecules. So the volume of that is going to be this thickness, average velocity times delta t, times by the area of that end wall. So this is the volume of molecules which can hit the wall in that time. So how many molecules does that correspond to? Well, it's going to be the total number of molecules in the whole box divided by the volume of the box. That gives you the number of molecules per cubic volume times by the volume of that place. So this number here that we're calculating, average velocity times delta t times area times number of molecules over volume, that is going to be the number of molecules that could hit the wall, that are close enough to hit the wall within the time delta t. Okay, so the molecules within range of the wall we could call call that, is the velocity, average velocity times delta t times the area times n over v. Remember again, what we're trying to calculate here is the momentum transferred per second. So we've got the momentum transfer per collision, and then we have the number of molecules that could hit the wall in that particular time. However, this isn't going to be all of them, because some of the molecules, although that's the average delta velocity in the x direction, some of those molecules are going to be traveling in the opposite direction during our time. So only half of those molecules will actually hit the wall. The other half will be going the wrong way. So what this number represents is the number of molecules that will hit the wall in times delta t, and every single one of them will transfer this much momentum to the wall. So if we want to find the force, we need to take these two things, the momentum transferred per collision times by the number of collisions in time delta t. Okay, so that's going to give us the force on the wall. So it's going to be change in momentum divided by delta t. Okay, so here's the change in momentum. It's momentum transfer per collision times number of collisions that took place in time delta t, divided by then delta t, because this top is momentum change and delta t is the time it took to do all that momentum change. So this would be the force exerted on that wall during the time delta t. It looks kind of a bit messy, but we could kind of clear it up a little bit here. First of all, we have a delta t top and bottom, so we could cancel those out. We have an average velocity here, an average velocity here, so we could multiply those two together. And of course, we also want to find the pressure rather than the force. So what we want to do is divide all of this force by the area of that end wall. So if we do that, that's going to simplify to 2 times 1/2 mvx squared n over v. Now I'm not cancelling out the 2 and the half just yet. So this is the pressure exerted on the wall, and at the moment it has mostly things we can measure. It has the number of molecules per in the whole box, and it has the volume of the box. But the average velocity of the average velocity of the particles in the x direction might be a bit difficult to measure. So let's take a look at that. So the average speed is a vector, and just like any vector, the magnitude of the vector is the square root of each of the components squared added together from Pythagoras. So the x component squared plus the y component squared plus the z component squared is going to give us the average velocity. And here we have the average velocity in the x direction. But the thing is, they're all moving randomly. So assuming they're all moving completely randomly, the average velocities in the x, y, and z direction should all be the same as each other. There's no particular reason they'd be going faster to the bottom or to the left or the right. So the average velocity should be in the x direction, y direction, and z direction should all be the same. So these three terms that I'm adding together are actually the same. So I could rewrite that as saying, well, the overall average velocity squared equals 3 times the average velocity in the x direction squared. So I could use that to put down here into this equation and get rid of this x component. So if I do that, my equation simplifies to this. I've got my v squared here, my vx squared is going to be 1/3 of the actual average velocity. So I end up with this. My pressure is 2/3 times 1/2 mv squared n over 2. And if you just look at this, of course you recognize, because what this is the average velocity of each molecule squared times the mass times a half, which is the average kinetic energy of the molecules. So 2/3 times the average kinetic energy of the molecules times n over v gives us the pressure. So that's kind of an interesting thing about pressure, is that pressure is actually a measure of energy density. That is kind of what it is. This is going to have the units of joules. N is just a number, and V is a volume. So pressure is energy divided by volume, which is another way of looking at it. So it's force divided by area, or you can think of it as pressure divided by volume. You can play with the units of that yourself and see that that is the case. So okay, so average kinetic energy of the molecules. How are we gonna work out what that is for any particular situation? The molecules are very, very small. There are like bazillions of them in even a small amount of gas. So how would we work out what the average velocity is? Well, luckily, that's kind of been done for us. And there was a scientist, Boltzmann, who kind of worked out a statistical approach for that. And what he realized was that the molecules in a gas follow a distribution, a statistical distribution of velocities within that gas. I won't go into the statistics, it's kind of interesting, but it doesn't. It's kind of outside the scope of this course. But basically, if you have molecules, ideal gas molecules, inside a container, and you have them at a certain temperature, they will have a random selection of velocities, but those velocities will be distributed like this. And you can see that as the temperature changes, the distribution will change. So the red one is cold, like a minus 100 degrees. See, the average velocity here is around 250 meters per second. As the temperature increases, that distribution changes. You get a wider spread of velocities, and the peak velocity, or the average velocity, increases. And so what he discovered was that average kinetic energy of this distribution changes linearly with temperature. So if you take any bunch of gas, you double the temperature in Kelvin, you will double the average kinetic energy. And the distribution is this: 1/2 kBt. So K here is a constant called Boltzmann's constant. It's a very, very small number, 1.38 times 10 to the minus 23 joules per Kelvin. T is the temperature in degrees Kelvin. And particularly, he noticed that the average kinetic energy is 1/2 kBt per degree of freedom. So what do I mean by degree of freedom? So if you imagine a completely featureless single atom on its own flying around, it can move in 3 directions. It can move in X direction, Y direction, and Z direction. Those are the 3 degrees of freedom. If instead you had a molecule that was maybe, shaped like a long-shaped molecule, maybe it's like a diatomic molecule, well, that can still move in the X, Y, and Z direction, but now this can also rotate in one direction and rotate in this direction. Rotating in this direction doesn't really do much, but rotating like this or like this, those are a further degree of freedom. So that would have 5 degrees of freedom. So if you had a simple monatomic gas, you'll have 3 times this 1/2 kBt, and basically every degree of freedom you get 1/2 kBt. So for a simple monatomic gas, what Boltzmann tells us is that the average kinetic energy per molecule will be 3/2 kBt, where T is the temperature in Kelvin. So we could put that back into our equation, because here we want the average kinetic energy. So we could replace this average kinetic energy with 3/2 kT. Why would we want to do that? Well, we want to do that because T is easy to measure. We can measure temperature. The average velocity of molecules is very difficult to measure. So if we plug this in here, we're going to get we're going to replace this kinetic energy, 1/2 mv squared, with the 3/2 kT. And hopefully you can see the 2/3 I have here is going to cancel with this 3/2. That's why I didn't cancel them out before. So what I get is this equation. P equals kT n over V, which if you've done any chemistry, for example, is likely to be very familiar to you. This is called the ideal gas law, and it relates the volume, temperature, and pressure of a fixed number of gas molecules together. And the ideal gas law applies very well to most gases, although we've worked this out on the basis of it being a monatomic gas, something like helium. It works pretty well for all gases, as long as the pressure isn't too high, as long as the density isn't too high, as long as there aren't other kind of extremes. This ideal gas law works pretty well in most situations. Now, you may be more used to it looking at it from the chemistry point of view. This is measured in number of molecules. In chemistry, etc., we don't tend to use number of molecules because that number is usually gigantic. So we tend to instead use moles, where a mole is the number of moles is the number of molecules divided by Avogadro's constant, 6 times 10 to the 23. We then also replace the Boltzmann's constant with something called the gas constant, which is just 8.3 joules per mole per Kelvin. And then we rewrite this equation like this: PV equals RTN over V, where this is now the number of moles and this is the gas constant. So, as I say, you've probably seen this before if you've done any chemistry, really. You may even have seen it in high school. But what I wanted to do today was show you how that actually relates to what we've been working with before in terms of momentum. This is a momentum transfer that gives rise to this equation. And it's kind of interesting this because although the equation was actually originally worked out before they even really knew about molecules, they just worked it out by measuring pressures and volumes and temperatures, it fits beautifully with this idea of momentum transfer for atoms. That was kind of worked out later, and it just happens to that it actually, it works. Okay, so we'll leave that there. This is now the start of looking a little bit more at temperature and where that comes from. But I just wanted to show how that links to pressure and momentum. And we'll leave that there for now.